Hi guys, lesson 1 again, but this is part 2 of the video. We just calculated this test statistic of 14.41, and we're seeing that we're having a number, but as always we try to quantify, is this an unusual number to get, or is it normal if the null hypothesis is true just from chance? What I want to point out though, if you have numbers that are close together, your observed and your expected values, you're going to get differerences close to 0. So if all of these observed frequencies were close to 15, then we would end up getting a chi-square test statistic that's close to 0, that's small. So it's interesting to see that we have a large number. I just want to know how large it is. We are going to end up using a chi-square distribution, which looks like this, to do this test. And just like there was a large count condition for our proportions test, there's a large counts for the chi-square test, but it's a little bit different. So it's going to be our expected counts. As long as all those expected counts, that order says the word counts, as long as the expected counts are all at least 5, your sampling distribution of this test statistic is modeled well by a chi-square distribution. And we already talked about degrees of freedom. It's the number of categories minus 1. So this distribution is a density curve. So it's a lot like the normal distribution or t-distribution in that respect, but it has a few different qualities. So first of all, it's only non-negative values. Only. So you'll see, unlike the normal distribution and the t-distribution, there's a there's a y-axis actually drawn to say, hey, we're going to always start at 0 because you can't have a chi-square test statistic that's less than 0. And then it goes infinitely to the right. You get these curves, like if I look at this one here, which is one with a degree of freedom of 3, it is very much not normally distributed. Specifically, it's very strongly skewed right. But then the larger your degree of freedom, the less skewed right it gets, but pretty much always going to be skewed right. So because of that, it definitely has a different shape, and it will have degrees of freedom like a t-distribution. So when we do this, we have to get p-values somehow, and there is a chi-squared table that you could look up. It should be in the back of your white stats book. You can Google it, or you can just use your calculator because they should all come with the function that we need to find the probability of being above a certain number. So for example, if I want to find the probability of getting a chi-square test statistic that is as large or larger than 9.8 with 5 degrees of freedom, then I'd be trying to picture a chi-square distribution with 5 degrees of freedom. So not really important, but the mean of a chi-square distribution will always be its degree of freedom. So if I kind of picture where the balance point would be for this, that'll happen at the degree of freedom. And then the mode, the peak of it, will always be the degree of freedom minus 2. So if you're trying to like sketch it slightly more accurately, you could do it that way. 9.8 would be somewhere up here. I would like the probability of being here or above. Well, every time we've tried to find the area below a curve, we've used some type of cumulative function for it, a Cdf function. So this is not a normal distribution, it's not a t-distribution, it's a chi-squared distribution. Therefore, we will be needing the chi-squared Cdf function in your calculator. Excuse me, this should be the same location that your other CDF functions are. So hopefully you can find it or Google it. Ooh, let's see if I can make this visible. So I'm going to go into my distributions and then do not choose PDF. We would like CDF. And then we're saying lower. Well, we want to go from 9.8 on up to a very large number. I usually use just 1,000. And then it asks for its degree of freedom. We said this one had 5 degrees of freedom. And then we can find the area of 0.081. So again, that was a lower of 9.8. An upper of very large number to simulate infinity. 5 degrees of freedom. And I got 0.081-ish. So like all other density functions, the area under this curve is 1. So if we know that this area is 0.081, we could find the leftover area in here. It does terminate, but we would know the area under that curve is 1 minus 0.081, but we are only concerned with the area to the right. Because when your observed frequencies are really close to what you're expecting, your differences will be close to 0, which is what I was pointing out earlier. If you get a lot of numbers close to 0 and you add them up, you're going to get a small test statistic, which means a small test statistic is giving you evidence that the null hypothesis is true. Because the null hypothesis is saying this that I'm expecting is what you're going to observe. So the null hypothesis is not likely to be rejected when you get a small test statistic. When you get large discrepancies between what you're seeing and what you expected, then you're going to have the differences that are large, and the test statistic will be large. Which means this region over here, any number over here, should not happen a whole lot if the null hypothesis is true. If you're supposed to be getting what you expect, then these will be very unlikely to occur. So a large chi-square test statistic is evidence for rejecting the null hypothesis, which means that this is always going to be a right-tailed test, which is kind of nice. You don't have to think about, is this left-tailed, right-tailed? Oh, I forgot, it was actually two-tailed. I didn't double my area. It's nice that it's already always going to be a right-tailed test. So the conditions for this test, most of them are identical to the ones we've always been using. We have to make sure we have a randomly selected sample from our population. We still have to check our 10% condition, since we will likely be selecting without replacement. So your sample size needs to be less than 10% of whatever your population size is. But then the large counts condition is still called the same thing, but it is slightly different. It's not n times p or n times 1 minus p. It's just that the expected counts need to be at least 5. So an example of doing all this at once. In his book, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it in the highest levels of the game, specifically because January 1st is the cutoff date for youth leagues in Canada, where many NHL players come from. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, more coordinated, and get more playing time, more coaching, have a better chance of being successful. So to see if birth date is related to success, judged by whether a player makes it in the NHL, a random sample of 80 players from a recent season was selected and the birth dates were recorded. The one-way table summarizes the data on birthdays for these 80 players. So we see that 32 of this sample were born January to March. April to June represented 20 of our players, so on and so forth. Do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year? So basically, is it true that the older kids in this group are more likely to make it in the NHL? Is there more in the older, or is it really just random chance and it's uniformly distributed? It doesn't matter when you were born. So I wrote out a bunch of this in advance because it's a lot of writing. So when I state my hypotheses, again, your null hypothesis is saying what you're expecting to be true is actually true. So you could say that the null hypothesis is that these birthdays for all the NHL players, you'll notice I'm putting all because I'm talking about the population. We're trying to make inference for the population, not just what my sample was. But for all my NHL players, we think it's uniformly distributed across the 4 quarters of the year. We're assuming that that's true unless proven otherwise. You could state this differently. You could say that the proportion of January to March is equal to the proportion of birthdays April to June. You could just say all these proportions are equal. So you will sometimes see that. And specifically, if I have these 4 quarters, we would expect them all to be equally representative since we're testing uniformity. So then your alternative was just that they're not uniformly distributed. Or you could say, since if we talk about the proportions, you could say at least 2 of those proportions are not a 4th. So some of them could be, they don't all have to be. There is no significance level stated, so as long as you do it before you run your test, you can really pick any level of significance. I'm just going to stick with 0.05 because it is the most common. So our plan, we are going to state what test we're using. This is the chi-square test for goodness of fit. I'm saying that I meet the random condition because the data came from a random sample of NHL players. I'm assuming it's the 10% condition. We must assume that 80 is less than 10% of all NHL players. Honestly, I have no idea if that's a reasonable assumption to make or not because I know almost zero things about the NHL. So it's still important to say what you are assuming to be true. If this was a true research thing, you are stating your assumptions. Other people who would examine your data could say, wow, this assumption you made is not true. You have it. Say what you're assuming. That's why we put this here. And then we need to test our large counts condition. Now again, this is about expected counts. So not the fact that we think it's a fourth. It's not based off of that proportion. It's how many I expect. So again, the total of this group is 80. So if I really expect it to be equally split into these 4 groups, I expect each group to be a fourth of 80, a fourth of this total in my sample size, which is 20. So that's what I expect. And so we could say all our expected counts, so we just did 80 times a fourth, all of these numbers are in fact at least 5. So because of that, we will be modeled by a chi-squared distribution, which is what we're going to do in our do step after we find our test statistic. So remember, the test statistic is to take what you observed, the counts that you observed, minus what we expected. We'll square that difference and then divide by the expected count. And then just do it again. So when you are equal to or just close to what you're expecting, you're going to have small numbers to be summing in, so that's not going to make much of a difference in our test statistic. The 16, though, is below what we are expecting. And the 12 is way below, not way below, relatively. So you could actually add these individually. I wasn't initially intending to do that, but this first number, 7.2, you are really above what we were expecting. Exactly what I was expecting. Because we squared it, we got a positive number here. It's really small, not contributing much. And the last one is a little bit bigger. So when I sum those all together, I'm getting 11.2 for my chi-squared test statistic. We're going to find our p-value, but we need to know what distribution we're using first. So there were 4 categories, so we will be using 3 degrees of freedom. So I need to be imagining my chi-squared distribution with 3 degrees of freedom. So we would know that this would happen at 1. This is poorly scaled out. So again, the balance point is always at the degree of freedom. The mode is at degree of freedom minus 2. That's just if you're trying to draw a nice one. If you want to know, you don't really need any of that information. But we need the probability of getting something as large as 11.2 or even larger than what we got. So we want the area to the right of it. And I should take the time to label what we have just sketched. It's not good to have an unlabeled distribution. So this is very much not a normal distribution. This is not a sampling distribution. This is the chi-square distribution, specifically the one with 3 degrees of freedom. So that's the area we're going to be finding. So we will find it using our calculator because we can. So I'm going to use chi-squared Cdf. Like I said, it's always a right tail test. Your lower value will always be your test statistic. And your upper value will be something very, very large. So when I put that in my calculator, I get about 0.011. Pretty small, but it's always quantified by comparing it to alpha, so it's less than alpha. So because our p-value of 0.011 is less than the level of significance that we said at the beginning, you always make your decision first about your null hypothesis. We don't continue assuming that the null is true. We don't think they're uniform anymore. So what we end up saying is we do have convincing evidence that it's just not uniform. that the birthdays of all NHL players are not uniformly distributed across the 4 quarters of the year. So we're basically saying that it kind of seems like the kids born at the beginning of the year, because they're older, bigger, they do maybe get more playtime. They get more representation in the NHL than the kids who are super young and possibly smaller and whatnot. So from here, you could do what's called a follow-up analysis. So what we just did is just testing the null hypothesis that this variable, the category variable, has a specified distribution in the population of interest. If the sample data leads to statistically significant result, like ours did, then we can conclude that it has something other than the one that was stated. It is not uniform. To investigate how the distribution is different, then you just got to be able to point out what happened with what you observed, essentially. So describing how far the observed and expected counts differ in those different categories, noting the direction of the difference. So for example, in our table of observed and expected in these NHL players, when we look at the components, the 2 biggest contribution to the chi-squared test statistic was this first January through March, and then also the October to December. So if you actually look at the numbers, when we look at the January to March one, there were 12 more players than what we expected. When you look at the October to December, there were 8 fewer players than what we expected. So this is supporting Gladwell's claim that the NHL players are more likely to be born early in the year. So if you were ever asked to do a follow-up analysis, that's all it's basically describing is we don't know what the distribution for the population actually is, but not only do we think it's not uniform, but it kind of seems like specifically, we get more older players